This is a very simple digital modes transceiver. Its direct conversion operates on 40 motors, both the FT8 and JS8 frequencies, and puts out about 700 milliwatts. The architecture is very similar to a double-sideband voice transceiver, except it's a little bit simpler. For instance, there's no microphone amplifier since the output from the computer is enough not to need one. Also, instead of a push-to-talk on the microphone, there's a manual switch on the front panel that does the transmit and receive switching. You have to keep an eye on the computer screen so you know when to flick from receive to transmit. The two crystals here are on 7074 for FT8 and 7078 for JS8. The switch on the front panel flips between those frequencies. The variable capacitor allows fine frequency adjustment, though in practice I never need to adjust that control. You could use a trimmer instead. The first transistor here is the local oscillator, followed by a buffer stage. That goes into a balance modulator, which works on transmit as a balance modulator and on receive as a balance mixer. It has 4 diodes, like the design in the Beach 40. You can just see 2 disc ceramic capacitors connected on one side of the transformer on the product detector balance modulator. One goes to the antenna for receive, while the other goes to some subsequent stages for transmit. Here's where it's a bit simpler than the Beach 40. The Beach 40 has 3 stages for an output power of around 2 watts. This has 2 stages for an output power of around 700 milliwatts. The driver is a 2N2222 and the power amplifier a BD139. The output from the final amplifier goes to the transmit receive relay, that rectangular box you can see here. The other connection from that goes to the receiver capacitor before it goes into the product detector. Connected directly to the antenna socket is a low pass filter for 7 MHz. That's a pi section, 3 all up. That cuts off any harmonics. Transmit receive switching is simple and manual. All the switch does is flick the relay on and off to change over the antenna connections. It also applies power to the driver and final amplifier on transmit and the audio amplifier on receive. I haven't mentioned the audio amplifier before, but that just follows the product detector and is used to lift the received signal up to a suitable strength for the computer sound card. It's the only gain producing component in the receiver chain of this circuit. Sensitivity is adequate on HF with a full-sized antenna. The transceiver has 4 connections: antenna, 12 volts power, sound in and sound out. These go to a Y connector which plugs into the laptop computer. The first test I did with this transceiver was before I'd properly refined it. Its output power was only about 50 milliwatts. Because it's double sideband, that's only 25 milliwatts per sideband. Nevertheless, I was able to make some FT8 contacts. And on JS8, I was able to have signals decoded by stations several hundred kilometers away. The challenge is to have an FT8 contact with another station, despite the low power and the manual transmit-receive switching. ZL is about 2,500 kilometers from here. Given the low amount of power, that's probably a couple of hops, so the greatest success is likely to come from single hops. distances of around 600 to 1,000 kilometres. We haven't seen very many other VKs come on right at the moment. They might come on a bit later on, and if they do, I'll give them a call. There's a VK2 calling at a reasonable strength, so we'll give him a go. With this amount of power, only about 50 milliwatts, it's only at the peak of conditions that you'd expect people to hear me. And in this case, I've been lucky. And VK2 VAR has acknowledged me and given me a report of -22. Now he's given me the report again. That must mean he didn't get my transmission just before. You've got to be quick on the switch if you're using this manual transmit-receive thing. And you can see on the map, he's a bit south of Sydney, not far from Wollongong. So that's quite a good distance, just with 50 milliwatts of FT8, or really 25 milliwatts. We'll just look at the list of stations. I want to talk a little bit about the final amplifier of this transmitter. Working back from the antenna connection is this low pass filter. Because it's low power, I'm just using 1 microhenry RF chokes, so no coil winding. I'm using polystyrene capacitors, and for a 7 MHz low pass filter, you want capacitance values of around 400 picofarads on the ends, and in the middle around 800. The nearest preferred values, which are fine for this application, are 390 picofarad and 820 picofarad. If you don't have 390, you could use something like a 330 in parallel with a 47. That will be near enough. Or for the 820, you could use, say, a 680 in parallel with a 150 or something like that. Now this type of low pass filter, it's got 3 inductors, so it's got a pretty good amount of harmonic suppression. You could use one with only a single inductor. In that case you'd have 390 picofarad on the sides and about 1 microhenry inductor in the middle, but the harmonic suppression of that isn't so good. A serious QRP rig would normally use around 3 inductors. If you're into reactance calculations and all that sort of stuff, the 390 picofarad capacitor will have a reactance of around 50 ohm, which is the input impedance, and the middle capacitor will have a reactance of 25 ohm, and the output, again, a reactance of around 50 ohm, that is 390 picofarad at 7 MHz, or near enough. Just one thing to bear in mind with capacitors and reactance is the smaller the capacitance value, the higher the reactance. It's a bit different to inductance, where the higher the inductance, the higher the reactance. The filter I've just described is one that has an input and an output impedance of 50 ohm. That's the most common design you'll see described, and that's quite suitable for transmitters with a 50 ohm coax output. The other thing we have to think about is the output impedance of the transmitter power amplifier. That depends on how much RF output you're getting, and also the voltage on the collector or the drain if you're using a field effect transistor. There is a very good tutorial on the design of all this by Paul Harden, NA5N, and there's a web link that I'll give in the video description. Anyway, it talks all about what you need for filters and output circuit matching, and it's got all the formulas, etc. One of the important formulas is what you're seeing right now. RL, which is the load resistance, equals VCC minus VCE. You work that out first, then you square it, then you divide it by 2 times the power output. The VCC minus VCE is basically your supply voltage minus a little bit of drop for the voltage drop between the collector and the emitter. 0.5 volt is typical. Let's assume some round numbers, assuming you're using a 12 or 13 volt supply. Let's say you've got 12 squared, which is 144, and you divide that by 2 times the power output. Let's supposing you're going to build a QRP transmitter with an output power of 1.5 watts. Then 2 times that is 3. And 144 divided by 3 is slightly under 50. Near enough to 50 for our calculations. That is a really nice number because it means that you've got 50 ohm output at the collector, which means you don't need any impedance matching at all between that and the input of your low pass filter. So bear that in mind. If you've got a 12 volt supply, then it's very easy to design a QRP rig with an output of 1.5 watts. If you're going to do this calculation, but for a bit more power, let's say 5 watts, then fortunately it's also fairly simple. The output impedance, instead of being around 50 ohms, as it was for a 1.5 watt transmitter, drops to around 13 ohm. 13 happens to be only 1/4 of the 50 ohm required by the output filter. Therefore, you can just use an output transformer that gives you a 4:1 impedance step down. Anyway, in this case, you've got 13 ohms on the collector, provides impedance transformation to 50 ohm, which is just what the filter needs. So that's very efficient, very good, and you can use a ferrite to do that. I'll just show you an example. You could use either a 2-hole transformer. This is a type that is commonly found in TV balance. You still sometimes see them on the streets with TV rabbit ears type antennas, or you can still buy these, or you can use a circular lifesaver type toroid. This tap is the low impedance tap that will go to your collector, which, remember, as I said before, was 13 ohm. 1 bit goes to your output, which is 50 ohms. That goes via a capacitor to the low pass filter, and the other goes to your power supply rail, 12 or 13 volts, with a suitable bypass capacitor. And that is exactly what you see in the circuit here. And you might also put in an RF choke just to get rid of any further RF floating around. Getting back to this transmitter, the output power is a bit less, around 700 milliwatts, so the load impedance will be a bit higher than 50 ohms. It will be something close to 100 ohm. Yes, strictly speaking, I could try and transform that impedance slightly, but I'm happy to tolerate a little bit of loss, so I'll accept it as is. It's not a radical impedance mismatch. If you were a perfectionist and didn't want to tolerate even a 2:1 impedance mismatch, another way you could get around it is to drop the supply voltage down to, say, 10 volts. That will drop the power output down a little bit as well. But what is important is this RF choke. You want to keep all the RF on the transistor side so that it can all be passed through the filter and thus to the antenna. You don't want it going over to the DC rail, where it would effectively be shorted to earth through your bypass capacitors. For 14 MHz, he's got that as 17 microhenry, and he mentions that the value is not all that critical. For these sorts of coils, around 10 or 11 turns on a bit of ferrite will do the job. You could use a FT8-43 toroid. That's about 12 millimeters or so in diameter, or this TV balun transformer thing. There's about 11 turns on here, and that's giving us 26 microhenry, which is perfect for this application. Here's a little trick. Even though resistors are not polarized components, it helps navigating the circuit if you do install them in a polarized way. By that I mean that the tolerance end that is the gold or silver band, goes to negative, or at least the lower voltage part of the circuit, and the first number of the value, the coloured band, goes towards the positive end of the circuit. It makes no difference to how well the circuit works, but it does help later debugging and repair, if you followed that convention in your projects. This is the following afternoon, 5 PM local, so it's still light. I've sorted out the transceiver and its output power is now about 700 milliwatts, so I should get even more success than I had last night. I gave VK2PWS a report of +7, he gave me -13. Flipping the transmit-receive switch got a bit tiring after a while, and it meant I couldn't use the automated features of JS8. So I put in a 2-transistor sound-activated relay circuit. That was modified from an item on the Talking Electronics website. At least the FT8 worked, with reports from 2 stations in VK5. My first real contact with the automated JS8 FT8 transceiver was with VK3YE in northwestern Victoria. That's a distance of several hundred kilometres. I should mention a thing about using this direct conversion receiver is that it will pick up other signals that shouldn't really be there. For instance, all this stuff is unlikely to be JS8 contacts. It's probably below. It could well be FT8 activity or even something else. That means that it's not a good idea to be using a very simple direct conversion receiver like this for serious DX reception. Nevertheless, I have received signals from Europe and North America with just the direct conversion receiver, but they're likely to be at a worse signal to noise ratio than if you're using a proper single signal receiver. Here's another contact further away, Ian VK5CZ. He's running 40 watts and I gave him +9. He's giving me +0. Which is pretty good given I'm running less than 1 watt and half of that is not even on the right frequency. Ian would be about 700 or 800 kilometres from here. This is a quick description of the double-sideband digital mode transceiver. It's very similar to a double-sideband voice transceiver, except there's some extra circuitry for the sound-activated relay switch. That's required so that you can automatically go from receive to transmit. In the top left, we'll have a close-up later on, but here is the crystal oscillator. It uses crystals from W6OUT that I reviewed previously a few months ago. One crystal is on 7074, which is FT8, and the other 7078 for JS8. There's a buffer stage following that, again an NPN small signal transistor. A balance modulator, product detector, I should mention on the right you've got what looks like a transformer. That's actually round on a ferrite. There are two windings of enamelled copper wire, about 0.5mm or so in diameter. 4 turns on one side, 10 turns on the other. And I'm using a 2-hole binocular ferrite type for the transformer, though you could use something like a T50-43, a ferrite toroid. On the transmit side, this is the driver. It's a 2N222, and then it boosts it up to around 800 milliwatts with this BD139. Very similar circuitry to that used in ZL2 BMI's double-sideband transceiver. Down here we've got the transmit-receive relay. There's two sets of contacts. One set changes the antenna connections over. The other set changes the DC power connections over. When the relay is pulled in, 12 volts is applied to the transmitter final amplifier and driver. When the relay is not energized in receive mode, you've got 12 volts of power going to the audio amplifier. Down here, the low pass filter for 7 MHz, so it cuts everything off above, bit above 7 MHz. Here is the voice activated relay, Vox, or sound activated switch, whatever you want to call it, and that is the one that switches it over to transmit when you've got a sound coming in from the sound card. Speaking of the sound card connections, you've got one connection, the sound card out, that goes into your diode balance modulator, which impresses audio upon the RF coming from the crystal oscillator, nulls out the carrier to get double sideband with the data signal superimposed on that. The audio also goes into this sound activated relay circuit. Just uses two small signal NPN transistors, and that's enough to drive a small 12 volt relay. On the receive side, you've got audio coming out from that same point, going to this audio amplifier, a BC548 or any small signal NPN transistor, and that goes to the sound card in. There's enough gain in this to provide reasonable sensitivity on 40 and 80 meters. For other bands higher up in frequency, you might need an RF preamp.